Dear Chairman, Honorable Assistants, good morning. Let me present you my contribution entitled Second Harmonic Generation in 5 Semiconductor Materials Periodically Structured. The generation of second harmonic is one of the nonlinear frequency conversion processes that can be strongly enhanced in photonic crystals, waveguides, and nanocavities. The 5 semiconductors are receiving more and more interest for their large second-order nonlinear optical coefficients and their large refractive index. Indeed, aluminium gallium arsenide is particularly interesting for second harmonic generation in the telecom range. The study of the photonic band gap evolution in terms of band gap width and positions allows the optimization of optical and geometric parameters necessary to obtain photonic band gap containing both the fundamental and the second harmonic waves. The plane wave method is often used for modeling the properties of photonic crystals due to it efficient for calculating perfectly periodic photonic crystal band diagrams. The propagation of electromagnetic waves studied in two-dimensional photonic crystals lattice requires taking into account the propagation modes in transverse electrical polarization TE and in transverse magnetic polarization TM. The expression for the second harmonic polarization is done so that the coupling between the fundamental wave and the second harmonic wave is not zero. We chose to polarize the fundamental wave in TE mode, taking into account the nonlinear tensor of aluminium gallium arsenide. The second harmonic wave is then generated in the polarization TM, and the nonlinear polarization term of order 2 is done. We calculate the two-dimensional triangular lattice parameters allowing the existence of the band gap in the TE polarization of the fundamental wave and in the TM polarization of the wave generated of second harmonic. Results are obtained by using a MATLAB curve with 121 plane waves. All simulations are realized for telecom wavelength. We clearly observe in Figure 1 the existence of several ratio values allowing the obtention of photonic band gaps both in TE polarization and the TM polarization. We can also observe that the position of the forbidden band in TM mode is double the position of the forbidden band in TE mode for each value of ratio. These results clearly show the possibility of generating a second harmonic wave propagating in the band gap in TM mode from a fundamental wave propagating in the band gap in TE mode. We notice that by fixing the AFI factor to 0.58, a very wide photonic band gap TE around the normalized frequency equal 0.3078 and a narrow photonic band gap in the TM polarization around the normalized frequency equal 0.5857 can be obtained. It is then possible with this type of a photonic crystal to simultaneously guide the fundamental wave and the second harmonic fields by fixing the period of the triangular lattice to the value of 457 nanometers. In conclusion, the theoretical study carried out through this work has shown the possibility of generating a second harmonic in a triangular photonic crystal based on aluminium gallium arsenide. Thank you for your attention.